Okay, so maybe it's time to start our today's meeting of the seminar on algebraic transformation groups. And I'm very happy to announce the talk by Immanuel van Santen. So it looks very promising, and the title is on the screen. Immanuel, please.
Thank you a lot to give me the opportunity to give a talk, to give an online talk. So I already write down somehow the structure, what I will do in this talk. So I will start with an introduction, then I will discuss basic notions, then I will come to the structure of Birx. So I will give some kind of structure result. Then I will speak about birational transformations preserving a vibration. I will come to Rosenlicht quotients in a more general setting, and then I will come somehow to the main points, Borel subgroups, and the characterization of rationality. So to set up to make a setup, I just say we work over a field K. So K is a field, and it is uncountable, algebraically closed, and the characteristic should be 0. So in principle, you can think of the complex numbers. Many results also hold for other fields without characteristic 0 and without the uncountability. But in order that I don't have to say for every result which one is which, I just say this one. Good. And once and for all, I will fix X. This is an irreducible variety over K. And something, if something is unclear, please directly interrupt me, okay? So that's, yes. Good. So the main protagonist in this talk will be the group of birational transformations of X. So this is the group of birational transformations of X. So in more algebraic terms, one can say these are the automorphisms of the field of rational functions of X. And the questions that I will address in this talk are the following natural questions. So the first one is knowing the birational transformations of the variety X. So in fact, if we know that this is the same as the Cremona group, so these are the birational transformations of the affine plane, does then hold that X and AN are birational. And that's the first one. And the second one are just what are Borel subgroups of Birx. Just one very, very general motivation. In the Erlangen program of Felix Klein, he said that one should study objects via their symmetries, or at least this is one kind of interpretation. So it's very interesting somehow whether the symmetries could determine an object. Of course, this can only happen if an object is somehow very symmetric. So in this introduction, I will say some kind of motivation words and some words about the history. Motivation and history. So for the first question, I would say this started in the 60s with Whittaker. And in fact, he showed if M and N are topological manifolds, okay? And if one has an isomorphism between the homeomorphism groups, N, okay, then this implies that there exists a homeomorphism G from M to N, such that the following condition is satisfied, that phi of F is the same as G, F, G inverse. Okay. And then later there came, this is by Philippe Krievich and Rybicki. There were other versions, mainly for smooth manifolds and diffeomorphisms. And I say and variants. So also there's a version for symplectic manifolds and symplectomorphisms and so on. So somehow the full analog statement is true.
So,
but
the groups are considered as abstract groups without any topology.
Yes, exactly. Yes, exactly. So but the topology will play a role. I mean, especially for the second question. But okay, this comes later. So in the algebraic setting, the I would say the analogous question to 1 would be sorry, in an algebraic setting and in an affine algebraic setting, the analogous question would be to replace the birational group by the automorphisms. And this statement is true, that if we have such an abstract isomorphism and X is affine, that then this implies that X is isomorphic to AN. This is due to Cantat, Regeta, and he. Then this result was generalization. This was generalization to affine toric and smooth affine spherical varieties. This is due to Andriy, Regeta, and myself. Good. So, but coming to the original question 1, in fact, this question is already so this question can be answered as true. So 1 is true, but under the additional assumption that the dimension of X is bounded by N, and this is result due to Cantat. Okay, so I mean, however, one has to say that imposing that the dimension of X is bounded by N is a very hard condition. So I mean, of course, one has much more flexibility if the X could be quite big. Okay. And in fact, one can also ask if some kind of an analog question, like here in Whittaker's result, is true, mainly whether every such isomorphism is given by conjugation. And of course, one can also act via field automorphisms. And in fact, for N equal to 2, then the analog of star is true. This is due to Julie Deserti. However, if N is greater or equal to N, the analog of star is false. And this is due to Tsikas. Okay. So that's somehow the motivation for studying this question, that somehow it is quite a harsh condition, this dimension bound. And somehow it would be nice to have a rationality condition purely in group theoretic terms. So yes. Good. And for the second question, let me also give some, let me also write some stuff. So first of all, I mean, everybody knows Borel subgroups. are important for linear algebraic groups. So they are just a quite important tool to study them. So it's quite natural to also study Borel subgroups of other transformation groups than just linear algebraic groups. And in fact, there is also some history about that. So in fact, if
So excuse me,
Yes?
could you please tell us what do you mean by Borel subgroups in this more general setting?
Yes, I will do. You mean about the topology, for example? Most probably, I think. I will define what Borel subgroup is, but I will do it later, okay? So far, you can think of, you have some topology on the birational transformation groups. I will speak about that, but I will do it later. So you have some topology there, okay? And then you can speak about connectedness, and then Borel makes sense. So it is a maximum.
Okay, you mean the same definition?
Yes.
Okay, thank you.
Yeah. Good. So Borel subgroups in the plane Cremona group. They are classified. We will come to this classification, and this is due to Jean-Philippe Furter and Isac Hedén. And in fact, it turned out that there are Borel subgroups inside these birational transformations of the plane that are non-conjugate. Okay, so this is different than in the automorphism settings. The Borel subgroups in out A2 are all standard. So I will say what the standard Borel subgroup is later, but there is some kind of a standard Borel that one has. I will come to that later. So in particular, this means there is only one up to conjugation. And this is due to Perez and Eshmatov. Good. And there was a conjecture around, or still it is around, conjecture of Popov and of Furter and Hedén, which says the following, that here an, as long as n is greater or equal than 2, has non-conjugate Borel subgroups. And the same for out an, but now for n greater or equal than 3, because for n equal to 2, they are all conjugate. Okay, so that's a conjecture. Good. So I thought, I mean, of course, I will tell you some some kind of results and so on, but I think it is very important that we somehow speak all of the same. So I will start with some basic notions that will be important for this talk. So basic notions. Okay, so the first notion is the notion of an algebraic family. Algebraic family of birational transformations. So what I mean with this, for this one has to fix some variety A, okay? And I look at the birational map of A times x to A times x, I call it Data, which is defined over A, okay? So meaning that when I project to A, the diagram commutes. But I want to have something more. This birational map induces me an isomorphism between U1 and U2, between some open-dense subsets. And what I want is that when I project to A, this is really surjective. Okay? Why I want this? the reason is that if I have such a thing, I can now look at the following map from A to the birational transformations of X. I can send, namely, A to X is mapped to theta of AX, okay? And this now makes sense because I have for every parameter A, this theta is defined somehow on the slice A times X, okay? That's the reason why I want that this really surjects. Does it make sense or yes? So, and all these kind of maps I will call morphisms. So this is a morphism. And the image I will call an algebraic subset. So this is an algebraic subset. Good. So these are the algebraic families, and the morphisms and the algebraic subsets. So now, having this, we can look at a topology on the birational transformations, and this we call the Zariski topology. So, sorry, Zariski topology on the birational transformations. So this is the finest topology such that all morphisms row from A to peer X are continuous. So I would say if one looks at the standpoint that one is interested how somehow birational transformations can deform, it is a natural topology for the group of birational transformations. Okay. And another notion, if I have some closed algebraic subset in peer X, closed algebraic subset, it would be nice to have a topology, to have a dimension. And in fact, the dimension is just defined as the topological Krull dimension. Okay, so this means just one looks at ascending closed subsets of V, and somehow the biggest such possibility is the Krull dimension.
So the first 2 points in your definition, this diagram and the next, are they the same as in Serre?
He also assumes that it is surjective down.
Eh?
Does he or not?
I think so.
I think as well. I mean, the point is, if one speaks about groups, so if this is a group and if this is a rational group action, then one doesn't have to assume this surjectivity.
Okay.
So then that's too much. But if I don't have a group, I prefer group.
So Serre was working with group actions and not with abstract families. Yeah?
Yes, and therefore he probably didn't assume that.
Okay,
it is proved that then this will be surjective for groups and group as a rational group actions.
Okay, thank you. And for this last definition, what is a simple example when this is closed algebraic, but not algebraic variety as abstract? So V and not A capital.
Also, you would say a simple example, which is
so the image of A, row of A,
yes,
is it closed algebraic or not necessarily?
This doesn't have to be closed in general, no.
Okay. But assume that it is closed.
Yes.
Can I then say that V is particular case of A.
As that you can deduce some information about A from V, or
okay. So it cannot be considered as abstract algebraic variety aside of bir X.
no, as the V itself doesn't has an algebraic variety structure.
Okay, okay,
yeah, no,
thank you.
no. But okay, this is a good point. So first of all, if I look at out X, so for out X, one has similar notions. Okay, but for out X, then this would be just an isomorphism. Okay.
Okay.
And yeah, then of course U1 and U2 could be just an A times X, and this is A times X. Okay, and I have a notion of morphism, algebraic subset, and so on.
Okay.
So for the very special case now, if X is affine, then the automorphism group of X has the structure of an int group. So I can write it as, I write it like this. And these HDs, they form a filtration. So I have H1 in H2 and so on. This is a countable filtration. The union of all them is out X. But now each of these guys is an algebraic variety. In fact, the affine algebraic variety. Affine algebraic variety. And each filter set is closed in the next one. Okay. And in fact, this filtration one has on out X can be chosen such that it is compatible with the group actions. So the group action, so somehow the group multiplication respects this filtration, and also taking inverse. Okay, but I have to say something more about this int group structure so that it is unique. So it has such an int group structure, okay, such that the following holds. The morphisms from V to out X. Maybe I should call them A. It's maybe better. These are the morphisms. The are the morphisms from A to HD for various Ds. Okay, so if I have a morphism from A to HD, then of course HD is in out X. So this means I have a map from A to out X, and this is then exactly a morphism in that sense. Okay. But on the other hand, if I have a morphism in that sense above, then it factors through some HD in the sense that this is really now a morphism of varieties. So in this context, somehow closed algebraic subsets are really algebraic, I can see as algebraic varieties, okay? But this is different in this Beer setting. So just that you have maybe some idea how one can cook up such a filtration for an affine variety. One can take somehow the most, let's say, as the most important affine variety, or I don't know, the mother of all affine varieties. So I can write it down as a limit of these are all affine varieties, and these are exactly the automorphisms of a degree less or equal than D. Okay. Good. So, but the point is, if we look to the birational transformations of AN, then the situation is different. And here, in fact, these birational transformations, they form not an int group. So this one is not an int group. Okay, this is due to Blanc and Furter. So just an int group is something that I said here, okay? It's just like a filtration of affine algebraic varieties compatible with the group action. So far, so good? Or?
Yes.
Good. So, in fact, this is a bit sad that this Cremona group is not has not the structure of an int group. But in fact, it has a structure which is quite similar. And this was also in this same paper. It was written down. And I will write down now the general theorem. This is now due to Andriy, Regeta, and Christian Urech and myself, but I will not write down every time that this is now our result because, okay, maybe I can, then it is clear. So this is Regeta, Urech, and myself. So in fact, there exist closed morphisms pi d going from HD to Urech for all d greater or equal than 1, such that the following holds. So the images, they exhaust the birational transformation group. And in fact, it is increasing union. So increasing. Okay. And in fact, Urech has the inductive limit topology with respect to these closed subsets, also to this closed filtration. So it seems a bit like almost an int group, but not completely, okay? And the second thing is, in fact, all this data, all these closed morphisms, they have enough information to get all the morphisms to Urech. So for all morphisms rho from A to Urech, there exists an open covering AI of A, such that the following holds. For all I, there exists a DI and a morphism going from AI to HDI with the following property, that going from AI to HDI and then via PDI to Urech, this is exactly the restriction of rho to AI. Okay, so in some sense, morphisms, it's not true that the morphisms are exactly the morphisms to HD, but somehow one has to take an open covering of A, and then somehow locally it is satisfied. Okay, so it is some kind of a bit more general thing than for int groups, but still I would say it is quite near of an int group. Okay,
but still HD are honest algebraic varieties.
yes, exactly. Yes, yes, yes. These are honest algebraic varieties. Yes, yes. But it's not.
And what is the difference? Why it is not an int group? What condition we don't have?
The point is that these pi d's, they are not injective.
Ah, okay. Thank you.
Yeah.
And this is a principal problem, or somebody else can prove that this is a real honest int group?
No, there are guys who proved that it is not possible that it is an int group satisfying the universal property, as the analog universal property as for the automorphism of an affine variety. So it's definitely, it is not possible to give it an int.
There is Blanc-Furter theorem, which is
yes,
written
yes,
there.
yes, yes.
Okay.
but still, for me, I would say more interesting than that it is not an int group is that it is almost an int group, I would say, because this gives some tool to study the group. Good. So I will write down some consequences of this structure theorem. These are not direct consequences, but one needs again some other stuff. So one consequence is about neutral components. Neutral components. So if G in X is a closed subgroup, then the connected component of the identity, this is in G open and closed and of a countable index. Just to say, this has nothing to do with the uncountability of the ground field, or so. Also, this theorem works over any algebraically closed field. Okay, so this consequence is quite more or less straight. So this is not straightforward. So this is not such a huge consequence. But this consequence needs more. The next one that I want to say, and in fact, there holds a Chevalier type theorem. Chevalier type theorem. What I mean with that, so if rho from A to X is a morphism, and if C in A is constructible, okay, that makes sense, a constructible subset, then the image is again constructible. This is then in X constructible. And there is a certain fiber dimension formula. Fiber dimension formula. So this is again for a morphism rho to X. So this is a morphism. There exists a U in A, which is open and dense, such that the following hold. If I look at the local dimension of U intersected with rho inverse of rho of U at U, and this holds for all U in U. So this is really the local dimension at that point. Okay, this is a closed subvariety of U, so that makes sense. This is the same as the dimension of A minus the dimension of the closure of the image of A. Okay.
And when you say connected component, this does it coincide with the path connected?
What do you mean by path connected? That you
I
can...
mean, when you use just the irreducible varieties.
Yes, yes, this is true. Yes, yeah.
Okay.
And we have another consequence. So just to say, these two consequences, they use also some kind of the approach of Hanamura of flat families of birational transformations. So it's some kind of a bit more involved argument. And the next one was even a bit more involved. So this is about algebraic subgroups. Algebraic subgroups. So if G in X is an algebraic subset, and it is also a group, okay, then G has a unique structure of an algebraic group. So this is also, first of all, this statement here, this was for Jean-Philippe, Furter and Jérémy Blanc. They proved that theorem as well, but only for the affine space, also only for rational varieties. Okay, and this theorem they proved as well only for rational varieties, and in fact, at least due to Jean-Philippe, this is somewhat the main result of that paper. And yes, so this holds as well also in full generality. So this is, yeah. All these things are in the paper that we uploaded yesterday. So it was today on archive. So yes. Good.
Excuse me,
Yes.
Immanuel.
Yes,
May I
hi.
ask you, yeah, hi. If when you say that G has a unique structure, you mean that you take an abstract group without any relation to the variety of the birational or the group of birational transformations. So this abstract group has a unique structure for the algebraic group. Is it so?
I'm not 100% sure whether I understand you correctly. So what I mean with it is that I have an algebraic group, and I have a morphism from that algebraic group to Bir X that has as image G. And now every morphism that has his image inside G will factor through this algebraic subgroup.
Okay, thank you.
Through this algebraic group. So in particular, it will be unique, this structure. Yeah.
Thank you.
Good. So these were the things that I wanted to say about the structure of the birational transformations. So I see the time is a bit running. So okay. So the third chapter is about birational transformations, preserving a vibration. So there, okay, the setting is the following. I have now some dominant morphism of varieties. Okay, and I take K as the algebraic closure of the function field of Y. So I can look at the geometric generic fiber of this pi. So this is just like I make the pullback to spec of K. Okay, I don't write spec of K, it's otherwise I have to write too many things. So this is the geometric generic fiber. And what I assume is that this guy here is integral. Okay. And this is in fact equivalent to the following assumption that K of Y is algebraically closed in K of X in characteristic 0. Okay, I don't speak now about positive characteristic stuff. There is a bit, the stuff is a bit more involved. So, and I look at the groups of birational transformations so these are the phi's, such that phi gives the fixes all the fibers of pi, and I can look at the group that somehow permutes the fibers of pi. So so there exists a phi bar in Bir Y, such that when I look at this phi bar ring pi, okay, so that such that this condition is satisfied. Okay, and the result we came up with is the following. So again, this is in that paper. So I have a natural map from XY to Bir Y, just by sending phi to its induced map, and this one is continuous. Okay, and the second statement is that going from the birational transformations. Sorry, I messed it up. So this should be like this, and this should be that one. I can go to the birational transformations of the geometric generic fiber. Okay, so they are now defined over this big field K. Okay, and this one is continuous as well.
So I don't understand. The second, in the second case, phi bar is identity, no?
Yeah, no, sorry. First I wrote the wrong group.
Okay.
So I really start with this group here. So it just induces something.
Okay,
I'm sorry.
Okay. It's permuted fibers, and the other one fix each fiber.
Exactly. And because it fixes each fiber, it induces the identity on Y.
Yes.
So I can make a pullback to K, and I get a birational map of the geometric generic fiber.
Okay.
This is this phi K.
Okay.
And I say this map here is continuous. This will be important then for the arguments. Okay. And another thing which is quite important is the following theorem. So if I have some sigma in here xy, okay, and sigma is not the identity. Okay, that is not important. I can forget about that. So then, in fact, this sigma is unipotent if and only if the pullback to the geometric generic fiber is unipotent. Okay, and this was another statement that, again, in the same paper. So this is another statement that is quite important then for us.
So you pass to non-closed field, yes?
No, the K is the closure of K of the function.
Algebraic closure.
Yes, algebraic closure. Yes.
Okay.
Yes. Yeah. Okay. And in fact, but maybe this is a bit too much because the time is a bit running. In fact, one could ask this question here, whether this also holds. I mean, this is some statement about GA, okay? But one could look at the analogous statement about GM, about the multiplicative group, and there it's wrong, okay? There are somehow easy counterexamples, but for unipotent, it's true. So I can see unipotentness on the geometric generic fiber. Okay. So the next tool that I will use, and this is the last tool that I want to show you, is about Rosenlicht quotients. Rosenlicht quotients. So for that, I just take G. This is in peer X, closed connected subgroup. Then the theorem is as follows. There exists a Rosenlicht quotient for G. And what I mean with that, so there is a U in X, which is open and dense and G stable. And as well a morphism pi from U to some variety Y, such that the following is satisfied. Somehow the usual condition of geometric quotient. So pi is surjective and open. And every fiber in X is a G orbit for all Y in Y. And the second thing is about the invariance. So for all, U is a bit a bad thing. So let's say V in Y open, the following holds. I can associate to a regular function on V. I can pull it back via pi, and then I get an invariant function. Okay. And this one is in fact an isomorphism. And moreover, the geometric generic fiber is integral of this pi. So this means that k of y, which is k of xg, this is in fact algebraically closed in k of x. So this is a Rosenlicht quotient statement for birational transformations. And the following corollary will be useful. So in case G is commutative, and it has no invariance except the constants, then the following points are satisfied. So G is an algebraic subgroup. The dimension of G is x. Is the dimension of x, and G is self-centralizing. Self-centralizing. Okay, yes. So this condition here just says that G acts with an open orbit via this Rosenlicht quotient theorem. Okay. Good. So this is the tool about Rosenlicht quotients. So now I will come to Borel subgroups. Borel subgroups. So yes, maybe I recall them. Okay. So recall.
Sorry, a silly question.
Yes.
What is self-centralizing?
Excuse me, I didn't understand.
What is self-centralizing?
Aha, it's just like if you take the centralizer of G, it is again G. So all elements that commute with G are already inside G.
Okay.
Yes. So a subgroup of some group as a subgroup B of some group that also is a topological space is called Borel. If it is a maximal connected solvable subgroup. And in fact, just for notation reasons, the zeroth derived subgroup of B is just B. And then inductively, I can define the ith derived subgroup just as the commutator of the derived subgroup before. And solvability means, of course, that somehow this group is trivial for some I. And in fact, the length of B will be just the minimal such I. So the I such that this one here is trivial. So, of course, there are famous examples. So one can take the upper triangular matrices. So, okay, inside G-ln. So, and here the length is, in fact, it depends logarithmically on n. and is in fact smaller or equal than n. This we will use later. So we will only use that it is smaller or equal than n later. And the second thing, and this will be the standard Borel subgroup in birational, this is the following. So these are all birational maps of that form. x1 to xn is mapped to a1 x1 plus b1 until an xn plus bn, where ai, bi, these are rational functions in the variables before. And I want that ai should be non-zero. Okay, so just, I mean, I wrote it here a bit shortly. As a1 and b1 are constants, but a2 depends on x1 and b2 as well. Okay, and this is in fact also a Borel subgroup, and the length of that Borel subgroup is 2n, and this is due to Vladimir Popov. And this is somehow the standard Borel sub. Also, this is somehow considered as the standard Borel subgroup inside the Cremona group. And the third example that I want to mention is this classification. So the Borel subgroups in the plane Cremona group. These are the following. So first of all, it is TF. This is defined as the maps of the form XY is mapped to AX plus BF over BX plus A, and then Y. Okay, where AB, these are rational functions in Y, and one wants that AB is not equal to 0, 0. And the F, this is also a rational function in Y. It is square free. And one wants that x square minus f of y, the zero set of this. Okay, this should have genus bigger than 0. So it should not be a rational curve. So this is somehow one family of Borel subgroups in Bir A2. And there is one special guy, this one here. So what if one takes for f the y, so this doesn't belong here to this one here. And then of course also the B2. And this is the full classification of all Borel subgroups in the plane. So this is due to Furter and Hedén. Okay, so now if I would be interested in constructing somehow Borel subgroups that are non-standard, also in higher dimensions, I think it is good to understand also somehow something about in dimension 2, because somehow yes, this gives some kind of motivation. So observe for E non-zero. So we are now in this case here. Okay. So this AX plus BF over BX plus A, this is equal to AX if and only if I can take it to the other side. I can multiply with it, and then I can erase with AX. So what I get in the end is F, and then I can divide by B. So what I get, this is satisfied if and only if F is equal to X squared. Okay, but somehow these points here, they form a curve that is not rational. Okay, so in particular we have that the fixed points of this map, I call it, let's call this map phi AB, of phi AB, contain a non-rational curve. Okay, but if I take any birational map, from A2 to A2, never contracts a non-rational curve. So I can say all these phi AB are not conjugate to elements of B2, because the fixed point sets of elements of B2, they are somehow rather easy to understand. They are in fact rational curves. Okay, so therefore it cannot be that this phi AB is conjugate, sorry, not conjugate to elements of B2. Okay, so yes, this gives some motivation somehow to look at this behavior here in higher dimension. So now if n is greater or equal than 2, I can replace just this second variable y by several other variables. So this means replacing a1 times a1 by a1 times a to the power n minus 1. Okay. And now I can look at the similar birational transformations. Okay. And I use the following ingredient. So any birational map from an to an, any birational never contracts, also sorry, I should say like this, any birational map contracts only ruled hypersurfaces. This is due to the weak factorization theorem. Okay, and then again one can say this phi AB, okay, with just the same notation, but now the y is somehow replaced by n minus 1 variables, is never conjugate to elements of Bn. Again, the fixed point hypersurfaces of elements in Bn are all ruled hypersurfaces. Okay. So this gives
Sorry, can you explain again this two lines? In one line, you say that fixed point set contain a non-rational curve. In another next line, never contracts non-rational curve. What is the relation between these two statements? So
no, sorry. Maybe my handwriting was wrong. So here I say never. So if I have a birational map from A2 to A2, it cannot contract the rational curve.
No, I understand. But what is the relation to the fixed point set?
This means somehow if I conjugate now this map here, this phi AB with some birational map,
yes,
it still has a fixed curve which is non-rational.
Okay.
Because somehow this fixed curve.
Of course. And what? Okay.
And now it cannot
disappear after conjugation with birational. Okay, birational conjugation cannot contract this one. Okay.
Yes.
Thank you. Thank you. So
And
this
this-
is invariant. This is invariant of conjugation.
Yes, exactly. And here it is a bit, it is somehow a bit similar. So maybe orally I say a bit more that this phi AB has fixed hypersurfaces that are not ruled. So one can take somehow a good F so that this fixed hypersurface is not ruled. But if I take a birational map from AN to AN, this only contract ruled hypersurfaces. So
Yeah.
again, this fixed hypersurface survives.
Yeah, sure. Yes.
But this gives the motivation. Now, if I would know that somehow I could embed this phi, as a phi AB belongs to some commutative group, and in fact a connected commutative group. So if I could enlarge it so that it becomes a Borel subgroup, this Borel subgroup, of course, cannot be conjugate to the standard Borel subgroup.
Yeah, okay.
But the problem is that if I take bigger and bigger stuff, bigger and bigger solvable subgroups, the derived length could be bigger and bigger and bigger. So that's the problem.
So there are examples of any derived lengths?
No.
No.
And this is the next theorem. So in fact, this is again due to us. This is not in the paper that we uploaded, but we will upload this soon, maybe this week or next week. So G in Urech is a connected solvable subgroup. And let's say n is the dimension of X, then I can bound the length. Then the length of G is smaller or equal than 2n with equality if and only if X is rational, and G is conjugate to a subgroup of the standard Borel subgroup.
So
Okay.
there could be really smaller subgroup than Bn of the same length. But G is not Borel, yes.
No. I just say I take any connected solvable subgroup.
Okay.
Then the length can be bounded by 2n.
Okay.
Okay. And I say when equality holds, then this G is, then first of all, the X is rational, and the G is conjugate to a subgroup of the standard Borel subgroup.
Yeah,
Okay. So with this theorem, as an immediate corollary, one gets non-conjugate, as one gets Borel subgroups that are not conjugate to the standard Borel subgroup.
Yeah,
okay, because with the argumentation I said before, so I can take this TF in higher dimensions. Now I can take somehow by a Zorn's lemma, I can take bigger and bigger solvable subgroups, but this becomes stationary because this will stay closed and connected, but somehow the length cannot increase arbitrarily high.
Yeah.
Okay. So I introduced many tools before, so I would like to give some sketch somehow of this at least for the first part, so that that you have some idea somehow how this works, that one can construct non-conjugate Borel subgroups. So sketch for the first part. So when n is equal to 1, okay, we speak about curves. And then these birational transformations are they are good to understand. So, I mean, here, of course, one can directly check that it is true. So there's no problem. So we assume that n is bigger than 1. And in fact, the idea is to proceed via induction. So let's say K, this is the length of G. Okay. And let's say A is the last derived subgroup that is non-trivial, and I take the closure of it. Okay. So this is inside X, a closed commutative subgroup. And then I distinguish two cases. So the first case is that the invariants are just trivial. And the second is then, okay, they are non-trivial. Okay, so what happens in this case? So as I said before, maybe I can go slightly back to the Rosenlicht statement. Okay, so if this one here is satisfied and if the group is commutative, I can say it is an algebraic subgroup of the same dimension as the variety and G is self-centralizing. Okay, so I can get that. So in this case, A is algebraic, self-centralizing, and the dimension of A is the dimension of X, which is in fact n. Now I can look at the following homomorphism from G to the automorphisms of the algebraic group automorphisms. I just write them like this, but with this I mean algebraic group automorphisms, where I just send the G to its inner automorphism. So A is mapped to G, A, G inverse. Okay, so this homomorphism has kernel A because A is self-centralizing. Okay, and in fact, when I look at the connected component of this group here, this is something that is contained in the connected component. Now I can take the affine part of this algebraic group and take the connected component of that. And this one here. And so this is just the affine part of the algebraic group, and this is the anti-affine part of the algebraic group. And I have an injection when in fact A is spanned by these two subgroups. Okay, and both subgroups are preserved under algebraic group automorphisms. Okay, so I get a map from here into that product, which is injective. Okay. So this group here is in fact trivial because I take the connected component. And this one here, this is in fact some GLD over K. And in fact, the D is just the dimension of just somehow of the unipotent radical of this GF. Okay, so in particular, it can be bounded by n. Okay, so this means that in fact the length of G, this is smaller or equal than the length of A plus the length of plus the length of the, let's call this psi, the image, okay, under psi. But this length here, this is 1. And this length here, okay, can be bounded by the length of a biggest solvable connected subgroup of GLDN. So this can be bounded by n. So this is less or equal than 1 plus n. So this is less or equal than 2n. And so this is what we wanted. So this was somehow the easier case. Okay. So let's come to the harder case. So this is B. So what happens if the invariants are not just only constants? Okay. What one can look at is now the Rosenlicht quotient. So pi from x to y is the Rosenlicht quotient, or a Rosenlicht quotient. Rosenlicht quotient of the A action. Okay, just I have to say x has to be shrinked. But of course I can shrink the x. This will not change the birational transformations. So I can really assume that this Rosenlicht quotient is a well-defined morphism. Okay, so now I can look at the map, let's call it phi. So G normalizes A, okay? Just remember that this A is just the closure of the last derived subgroup that is non-trivial. So G normalizes A. So in particular, it permutes the fibers of pi, okay? Because the fibers of pi are just A orbits. So this means I get a map to beer Y. So every G induces a birational map on Y, okay? And as I said before, this one is continuous. Okay. And I define H as the kernel of this phi. So this is a closed subgroup of G. So this is in G, something closed. Now, in fact, I have the following. The length of G mod H circ, so this is the connected component, is in fact the same as the length of G mod H. Here is some argument needed. Okay, I can show you this later, or I can somehow give an indication of this later. But this one here, of course, is the same as the length of the image. Okay, but now by induction hypothesis, okay, this one is a smaller variety. I can say this is smaller than twice the dimension of Y. Good. But I can now also look at another map, namely epsilon. This map, this goes, also all the elements of H, they induce on Y the identity. So I get a map to the birational transformations of the geometric generic fiber. Remember, this geometric generic fiber is integral. It's from a Rosenlicht quotient, sending just H to HK. And this map is continuous, as I mentioned before. Okay. And again, this K is just the algebraic closure of the function field as this big K. Now the length of H circ, this is the same as the length of the image of H circ. Okay. As this one is, in fact, also this is an injective homomorphism. Okay. But this one is now a connected solvable subgroup in this geometric, in this group of birational transformations of the geometric generic fiber. So I can bound it by twice the dimension of this geometric generic fiber, which is then just twice times n minus the dimension of Y. Okay. So now I can put everything together and get that the length of G can be bounded by the length of phi sorry, by this length plus this length here, okay? But when I bound them together, I get less or equal than 2n. Should I say something to that? It has to, here, this argument really has to do that the field is uncountable. Or maybe should I say something more about the characterization? Would you prefer? Is there some opinion?
Characterization of what?
Characterization, okay. Good. So this is the last. So characterization of rationality. Characterization of rationality. So the theorem is somehow a positive answer of the first question. So if beer X is isomorphic to beer AN and no other condition, then X and AN are birational. And in fact, a similar statement holds as well if beer X is isomorphic to beer P1, or I can also say A1 times Y, then in fact the X is birational to A1 times Z for some variety Z. So also ruledness is seen by the birational transformations.
Very nice.
Yes. And in fact, the main new ingredient here is the following. Main new ingredient, which is a little bit technical, but not too technical. So GH, and I will then show you how one can apply this. So GH, these are closed, connected, commutative subgroups. And they should be non-trivial, yeah. And I assume that G normalizes H, and H is covered by countably many G conjugacy classes. Okay, then the statement is the centralizer of H contains unipotent elements. So I think it's interesting. So why this theorem is interesting for this situation. So let's say just A, B. So for A, I take some isomorphism from beer AN to beer X. Okay, group isomorphism. And I take the translations. So these are just the translations inside beer AN. And I also take the standard torus. So this is the standard torus in beer AN. So of course, both act with an open orbit on AN, so they are self-centralizing. Centralizing. So in particular, the images are also self-centralizing. But when they are self-centralizing, they are in particular also closed because they are somehow centralizers of certain elements. Okay. And moreover, I have now an action of, I call this G, psi of the connected component of that image on the connected component of the image of the translations. Okay, and in fact with countably many orbits. Okay, so we are exactly in the situation of the theorem. Okay, so so this implies the centralizer of H contains, which is exactly this H here, contains unipotent elements. But in fact, every countable index subgroup of the translations is dense. Okay, so this implies that this centralizer of H is exactly only the translation, the image of the translations. Okay, so it is not something more. So this means this image of translations contains unipotent elements, but now I can use that in fact as a LAN acts on these translations without the identity transitively. So the same holds, of course, also for the images. And therefore, I know that all elements in this image are unipotent. Okay. And this is somehow the main the main point that in fact this whole translations goes to a subgroup of the birational transformations which is closed and contains only unipotent elements. Okay, and in particular, of course, it is then also connected. And then somehow the idea is to again to distinguish whether this group H has invariance or it doesn't have invariance. So if it doesn't have invariance, it's somehow the easier case, and the other cases somehow then again more involved and uses some kind of divisibility tricks. But I would to say the main point for us was definitely to have that this image consists only of unipotent elements. So yes, of course, a big question would be, what about countable fields? I didn't spoke so much about it, but somehow this uncountability was used everywhere all the time. And it seems to us that if one wants to do such things over countable fields, one has to make completely new, one needs to have complete new ideas. And so this seems to be really much more involved. So this is just at least our impression. So thank you for listening. So I will finish my talk.
Immanuel, thank you very much. So it was a very interesting talk. Dear colleagues, any questions, comments?
So there's a question.
Yes.
So you were speaking about Borel. What can you say about tori, algebraic tori, maximal tori?
As I mean, maximal tori in the Cremona group, as of
Yes.
dimension, and they are all conjugate.
No. There is an example in Popov's paper that in
No, of that. Wait, when I say of okay, oh, sorry. Sorry. Yeah. I say if the dimension is n in Cremona n, they are all conjugate. Yes.
As far as I remember, no.
No. No.
But this is Bialini-Pirula, no?
In our AN is Bialini-Pirula, but in Cremona it's a bit different, but still it's the answer is yes. So in Popov's paper, the counterexample was he has a torus of dimension n-3, which is not conjugate to a subtorus of the standard torus.
Exactly.
And
So
it
it has
just
lower
came
dimension.
from cancellation problem, yes.
Yes.
Oh.
Yes. It
Oh,
was
but
really a
it's
smaller dimension.
Yeah.
Oh, okay. Yes. And are there Borels without tori at all?
Is a good question.
In these examples that you presented.
What do we mean by, yeah, okay, the point is just in the example that I presented is somehow, I mean, I have a commutative subgroup and I can enlarge it to a Borel subgroup, but so far I don't know exactly what it looks exactly, this Borel subgroup. So one has to investigate there more.
But
So-
already in Jean-Philippe's paper, there are Borel subgroups without any algebraic subtorus.
Okay. Okay.
I mean, the question is what you mean by algebraic subtorus, but wait. I mean, here you have I mean, this is some kind of a non-split. I mean, this is some kind of a torus. It is just like a non-split torus. So if you also allow non-split torus, there are all half tori.
Mm-hmm. Okay.
Okay, please. Any more questions? Maybe some participants may comment on this result, some connected results. If not, then let us thank Immanuel again. So thank you very much for your nice talk. And
Thank you for listening and giving me the opportunity to speak.
okay, so dear colleagues, we hope to see you again for some next meeting of our seminar. So see you.
See you. Bye.
Bye.